Well, I don't typically spend a lot of time on naming. Naming benzene derivatives is a little bit different from other things, so we'll talk a little bit about it. If we want to name a monosubstituted benzene, we would name the side chain followed by adding benzene. So this would be bromobenzene. If I had a propyl group on there, it would just be propylbenzene. I'm not putting a number right now because the 1 is understood. It would be 1 propylbenzene, right? Or 1 bromobenzene. Just like in any ring structure, wherever the first point of attachment is, that's always 1. Now there's a lot of common names related to benzene because there are a ton of aromatic molecules and molecules based on benzene that we see every day. So a lot of them have common names that we should probably know. Methylbenzene, we don't ever refer to as methylbenzene, we call it toluene. Hydroxybenzene we call phenol. And aminobenzene we call aniline. Now what about disubstituted? In disubstituted examples, we can use numbers to explain where the different substituents are. So this could be 1,2-dibromobenzene. Well, this one would be 1,3-dibromobenzene. And this would be 1,4-dibromobenzene. Now, there are other naming systems that we use for aromatics that talk about the relative position of substituents on aromatic ring. So anytime we have things that are 1, 2, we will call those ortho, or we'll just use the letter O. 1, 3 substituents we say are meta to one another, or M. And 1, 4 substituents we say are para to one another, or P. So if I have this molecule, we'd name it as the base phenol, right? Remember that from before. And our chlorine is in the para position, so it would be parachlorophenol. There are two other things that are important in naming, and that is when we have a benzene ring as a substituent on something else. So make something large here. If I have just a benzene ring attached to it, I'll call this group here a phenyl group. However, if I have a group like that, it has one methyl first and then a benzene ring, then this whole big group here with the benzene ring and the methyl group would be called benzyl, or benzylic. So this then would be a benzylic carbon, and the hydrogens that are on that would be a benzylic hydrogen. Let's continue to look at reactivity and stability of benzene. We looked at it just a little at the beginning of this chapter. Let's take a look and see why benzene doesn't react the same as other alkenes. If you remember from the dienes chapter, we looked at heats of hydrogenation to compare the stability of an isolated versus a conjugated diene. We found out that conjugated dienes were lower energy. So if we want to look at the stability of benzene, we can compare it to cyclohexene, cyclohexadiene, and then benzene or cyclohexatriene. So to do that, we can hydrogenate cyclohexene with H2 and palladium and carbon to make cyclohexane. We can hydrogenate cyclohexadiene with H2 and palladium and carbon to also make cyclohexane. And then we can hydrogenate benzene with H2 and palladium and carbon to also make cyclohexane. Now, since we're making the same product every time, we can directly compare the energies related because the energy of the product will always be the same. So if we want to look at the heat of hydrogenation, delta H0, for each of these, the heat of hydrogenation for cyclohexene is 120 kilojoules per mole. These are all going to be in kilojoules per mole. What would we expect from cyclohexadiene? It has two alkenes instead of just one, so you expect it to be about 240 kilojoules per mole. However, if you remember conjugated versus isolated dienes, you know that conjugated dienes are slightly more stable, and actually it turns out that the actual energy there is 232 kilojoules per mole. If we're putting this on an energy diagram, where here at the bottom is cyclohexane, that's the most stable, Here's energy. And then up here, we have cyclohexene. Not quite double, so a little bit below double, we have cyclohexadiene. So this is plus 120. This is plus 232. So the question is, where would we expect to see benzene? And the place you'd expect to see it then would be about 360. So if one double bond is 120, two double bonds is 240, three double bonds should be 360. We might guess that's a little bit lower in actuality because there's some resonance delocalization, so we might think it's a little bit below 360. So where it actually is 208. It's in here. And this is where aromaticity comes in. We would expect it to be almost 3 times, and it turns out that it's even more stable than with only 2 pi bonds at plus 208 kilojoules per mole. This is the special resonance stability that you get in aromaticity, which we'll continue to talk about throughout this chapter. But this is what makes benzene and makes aromatic compounds so completely different. Their reactivity is different, everything is different about them, because they're so much more stable than you expect them to be.